Assalamu alaikum, guys. This is a continuation from our previous modulation schemes where we discuss ASK, PSK, FSK based on their binary values like BPSK, BASK, BFSK. Now we will discuss more general schemes. So uh, the first scheme will be PAM. So so in this scheme we called it pulse amplitude modulation with M array. Okay, so it's a actually amplitude modulation scheme, generalized, more general M array PAM, pulse amplitude modulation with M array. Now this is compared to the amplitude modulation or ASK or BPSK. They are actually all are B, like binary. There are two values there, so they are actually FSK also. They are actually we consider with two possible values, binary values. We want to see how the generalized scheme looks like. So first modulation scheme is the PAM, pulse amplitude modulation. Here the M denotes the M level. How many levels in, for example, in BPSK, BSK, how many levels we consider? Two levels, right? Now in M, so M is the M level that mentioned here. M denotes the M level. So M level pulse amplitude modulation. That's actually our very generalized modulation amplitude modulation scheme. So as usual, our transmitted signal was xt is expressed by a0 pt. Here a0 can take one of m different level. In previously, a0 could have taken maximum two different levels. Now here in m level or m array system, a0 can take one of m different level. M different level. And pt is the our pulse. For example, uh, because here the number of m is assumed to be more than 2, so how many bits are required? Here in m array system, in m array, any kind of m array system, instead of bit we will consider symbol. I'm explaining why. So the number of bits, we know how to calculate it. We know it by log base 2 with m. If that's the number of bit per symbol, so this gives you number of bit per symbol. For example, if m value is 4, m equal to 4, instead of 2, m is 4. So we will have what? 0, 0, 0, 1, 1, 0, and 1, 1, right? So 0, 0 will indicate level 0, level 1, level 2, level 3. So there are 4 level, right? So expressing 4 level, how many bits we need? We need actually 2 bits. So like from here, if m equal to 4, the number of bits per symbol will be what? Log 2 to the power 4 equal to 2. So we need 2 bits, like 2 bits, any 2 bits combination to express 4 level. If it's m equal to 8, then we would have been taken number of bits would be 3 per symbol. So this is simple. This in one symbol there are 2 bits. In one symbol there are 2 bits. So in M level, in N modulation scheme or M array scheme, instead of bit or bit, we will be using symbol. So this is a 2-bit word. The symbol contains 2 bit. It's a 2-bit word. It can be 3-bit word if M equal to 4. Sorry, M equal to 8. Okay. So now let's give an example where we actually will consider an example where we will consider M equal to 8. It's a good number. So if M equal to 8, then what will have a number of bits? Bits will be log 2 to the power 8 equal to 3. Okay, so there will be 3 bits to express 8 level. That's it's actually saying. Let's see how. For example, so if this is A, then this will be thrice A. This is 5A, 7A. Same thing. Minus A minus A minus 3A minus 5A minus 7A. Here we are assuming the distance between 2 are like any 2. So distance are between levels twice A. That's all. Right. So we consider M equal to 8, 8-bit word. Sorry, 8-bit level, 8 level. We need 3-bit. So it starts from like 000 up to 111. So there will be 8 levels will be there. So here these are our 8 possible levels. In this example, we assume every each bit duration is 2A. Okay, so our signal A0. So signal A0 belongs to plus minus A for this example. For this example, plus minus 3A plus minus 5A and plus minus 7A. Right? Okay. So in our example, the constellations are separated by 2A. Constellations are separated by 2A. Like constellation, this constellation and this constellation, they are separated by 2A. Also, from this constellation to this constellation, they are separated also by 2A. So for our PAM, this is the constellation. So for generalized, for a generalized PAM, general M array PAM system, for a generalized M array PAM system, A0 is expressed as plus 1A, where I is 0, 1, 2 up to M by 2 minus 1. Condition that this M is a even function, or it's an even value. Otherwise, you cannot divide it by 2, right? So for a generalized M array system, M is an integer actually. Even or it's an integer function. So let us actually our evaluation system will be same as the previous all the previous system. The way we did it, we also try to evaluate this scheme same way. So let us assume that average symbol energy. We are not saying bit energy because it's actually symbol. Each symbol contains 2 bits, 3 bits, blah blah blah. But here symbol is a unit. Symbol energy is ES. Previously, uh, we assume that our average bit energy was EB. That's the difference comes here. Okay. So if this is the case, then what is ES? Okay. So if then what is the average symbol energy ES? From this value we can find average. So we'll divide it by this m by 2. M by 2. So twice I, this one, twice I plus 1 A square, both because we are finding energy. So it will be square. So I value will be 0 to m2 minus 1 up to this value, from 0 to this value, right? We know that a0 is twice I plus 1 A, this one, this one. So this is our average symbol energy. Okay. Here you see A0 belongs to plus minus A, plus minus 3A, plus minus 5A, plus minus 7A, because they are in symmetry. That's why m by 2. So we can write here by symmetry. This is m by 2 is because of symmetry. So we can write here. We can write right here as a note that by symmetry, A plus A and minus A. For example, this case, plus and minus A will have same, will have same energy. That's why we actually divided m by 2, because we took the symmetry. Okay, so we can find the ES value. So we can solve the equation for ES, average energy. So if it's by symmetry, what happens to the previous equation? Oh, okay, there is a square here. Okay, so we will apply standard expression. Okay, so we will, by using, so by using the formula for sum of n integral integers and sum of square of n integer, we can uh, simplify the expression es. This expression es can be simplified by sum of integers, because this is sum of integers, and sum of integral square of integers. So it's a standard formula, right? Probably you know it already. Es is, we can write it again, square by m, just rewriting the previous equation. this equation. This was a plus b whole square, so that's I'm actually expanding a square plus twice a b plus b square. So now here we will actually apply this formula of sum of n integers and sum of square of n integers. It's actually standard expression. Like I equal to 0 to m by 2 minus 1 in our case I square. So we can write twice a square by m for m by 2 minus 1 m by 2 m minus 1 m minus 1 divided by 6 plus, so I expand this part, then 4 m by 2 minus 1 m by 2 by 2, right? I expand this part plus m by 2. So simple formulation. If you yeah, just twice a square by m, simple mathematics. Just trying to find the solution. M by 2 minus 1 plus m by 2. Okay, it will be 2 by 3 can be common. You can have m by 4 minus 3m square by 4 plus m by 2, plus m square by 2 and minus m by 2. Okay, so we will end up this formula. Okay, just again twice a square by m by 6 minus m by 6, which will be twice a square by m into m by 6 into m square minus 1, which is square 3 by, okay, this is standard derivation. Okay, so es, so energy per symbol will be a square by 3 m square minus 1. You can see that the energy per symbol is a function of a and m. It's a function of a and m, right? So this is our average symbol energy. We can find the a from here. So this is energy per symbol where we have 2 m level. Twice a is the spacing level. Okay, from here we can find a. We can find a. We can find a. Value of a will be nothing but 3 es by m square minus 1. So this is the average symbol energy of es. So this is the average average symbol energy of ES. So this is the value of A, right? So A ensures the average. So this expression is a fixed symbol energy. Yes. Okay. Here assume twice A is the separation. Twice A is the separation. Separation of the constellation or the various levels, whatever. Right now, we know already that our signal was xt. Our signal was xt a0 pt, right? Here, how we also the expression of pt is the standard expression twice by t cos twice by fc. You know it. So 0 t. Here, this t is different, r by fc. Or we can write k by fc. Before we use k. K is an integer. Integer. Here, this t is the before it was t was a this t sorry this t was a bit period. Now it's a symbol period or symbol duration. Okay. Now we also know or from previously energy of pulse ep was unity. We find it previously, right? So you'll assume that value. We're not going to derive it. So this is actually our transmitted signal. Up to this is our transmitted signal. So this signal will be transmitted. Now let's see what happens to a received signal. So receiver or M PAM. Okay. So we will be using matched filter because the match filter is modulation independent. Whatever the modulation scheme doesn't matter. The match filter always can maximize the SNR. For that, the condition we know HT equal to PT minus T, right? So match filter can always maximize the SNR without like irrespective of a modulation scheme or the number of levels, whatever. Only the pulse shape. The match filter works only based on the pulse shape. Okay, so we can apply the same mechanism to the higher number of array for uh, for this expression, right? So what will be the receive signal? Our receive signal we know r t after sampling t, capital T. So it's like a standard equation that we use several. Let's say so we will find ep plus n tilde. Remember we use this expression like many times. So after match filter. So RT is after match filter, the receive signal after match filter. Okay, so RT is the after match filter, which is be sampling at t equal to t. This is actually symbol now, not a bit. So here A0 we know A0 just we write few minutes back. Like A0 is nothing but twice I plus 1 A. And n tilde is nothing but the Gaussian distribution. We discussed about the characteristics of n is Gaussian noise, which has a mean 0. Okay, mean 0 and variance n 0 by 2 EP. EP is 1. So n0 by 2. Like we know about this noise very well now, because this is a additive white Gaussian noise with zero mean and variance of n0 by 2. Okay, now for decision statistics, how to find a decision statistics. Okay, so decision rule, how to decide who is what. Okay, for deciding, let us draw our scheme again. We have plus a, 3a, 5a, and 7a, right? Then we have minus a. In our example, we used m equal to 8. So we will have 8 level, minus 5a and minus 7a, right? The constellation duration is twice a. Okay, so the decision, how we take a decision, for example, between a and minus a, for example, between a and minus a, between a and minus a. So this is the boundary between a and 3a. This is the boundary. Likewise, for everyone have this boundary constellation. Everyone has a boundary. So for a and minus a, this is the 0. A and minus a, this is the 0 value. So a and between a and 3a, this is twice a value. 3a and 5a, this is 4a value. Likewise. Now from a to, from plus a to twice a, so this is twice a. If any value, for example, if our r receive signal rt lies between this boundary, right? Lies in this region, what we will decide. For example, our rt received signal lies in this region. What we will decide? We will decide the value or constellation is, received signal is a. So a0 will be received as a. Likewise, if rt received between twice a and 4a in this region, what we will decide? What will be our decision? A0 will be 3a. Likewise, so this is actually our m equal to 8 PAM system or constellation system. Right? So how we are deciding this one? So if r equal to this, if r equal to that, how we are deciding? We are deciding by closest neighbor. This is the rule. Decision rule is the closest neighbor. Based on this decision, we will actually decide. So here we can see they are in symmetry. Whatever happens, like this region happens on that region also. So by symmetry, I can say by symmetry, Symmetry. Let's say summarize the decision rule. If RT is greater than 0, RT is greater than 0 to twice A, means this region, to twice A. What is the decision? Decision will be A0 equal to A. This one. If RT is this region, in this region, RT is greater than twice A, greater than twice A to 4A. 4A, what is the decision? Decision A0 will be 3A. Likewise, that's why we say I'm not writing for others part. So whatever you decide in this region will be same as like this region will be same as this region. So this symmetry you do not I do not have to write repeatedly. So what is our decision rule is the closest neighbor. That's actually our decision rule. So what else? There will be 3A, there will be 5A. So for some condition, if so you fill up this condition. If this is this, then this side A0 will be 5A. When A0 will be 5A. If this is the condition, the decision A0 will be 7. This was 7A. Okay, 7A. Same thing will be different for like minus A, minus 3A, minus 5A, blah, blah, blah. So A0 has to be minus A0 has to be minus 3A, A0 has to be minus 5A, okay? And A0 has to be minus 7A. So all are the decisions. So how many cases will be there? Because it's a combination of M cases, right? It's a combination of M cases, isn't it? For each point, huh? So there are because we have M levels, so there will be M decision points, and our decision was based on the nearest neighbor rule. That's the decision. Okay. Now this is actually okay for. Okay, I made a mistake. This is not mistake. You see, for this point, up to this point, up to this, up to this, every constellation will have two neighbors. Either like you are in 3, so either it goes this way or goes that way, right? So every point have two constellation neighbor. Or for example, in your boundary, for example, someone is here, it has either this way or that way, except the last one, this guy, 7A, except minus 7A, which is actually the end point. So this 7A, and for this 7A, these rules are not valid. There has to be different rules, because all the points have two neighbors, isn't it? All the, for example, RT, if you are here, you have two neighbors, either 0 to twice A. You have 0 to twice A, right? Which is not valid for the corner or end point, because they only will have only one neighbors. So the decision rule will be different. So we'll see it how for corner points decisions are different. Okay. Okay, let's us draw for this endpoints again. Okay, so we are here, we are at a minus a whatever, then we go up to n point. What is the n point in our cases? N point, how we find n point? We find twice I plus 1a. That's how. Okay, I is the m by 2 minus 1. Yeah, you see here we say the end point. Why do we write the general one? Yeah, here. So a0 can be anywhere, depends on the I. If I is 0 and a was 1, right? I was 1, a was 3. Like how we find a, 3a, 5a, 7a, in this formula, right? So the last point when I equal to m2 minus 1, what is the a0 then? Okay, let's see. And the a0 was twice I plus 1a. I equal to m2 minus 1. So what should be the I value is m minus 1a. So the last point is this point. For example, this is the last point. So this is the a0 m minus 1a. Or for example, in this end, this is a0 equal to minus m minus 1a. What was the previous point then? If this is the last point, this will be m minus 3a. Same thing, minus m minus 3a. What is the neighbor? What is the boundary between these two? Here is the boundary. Here is the boundary. What is the boundary point then? Boundary point is m minus 2a. You see, it was m minus 1a. So previous one will be m minus twice a. The previous one will be minus 3a. Same thing. So here the boundary is minus m minus twice a. So here is the difference. You see, if RT is greater than m minus twice a, then this side is equal to m minus 1. Same thing, if RT is greater than minus m or this value, then this side, this is the constellation. This side, this is the constellation. You see? Now condition changes. Previously, in these points, they have two neighbors. Here, it have two neighbors, two. But here, it have only one condition. Okay. So this is only for the end points. This actually our end points. For example, this is and this is actually end points. For end points, so end point decision rule is little bit different, right? Okay. So what was our decision? If so RT is, for this case, RT is greater than RT is greater than m plus m minus 2a, this side a0 equal to m minus 1 means n, sorry, m minus 1a, this side, this the end point. Or if the opposite one, if rt is here, rt is greater than minus, rt is greater than minus m minus 2a, then this side is equal to minus m minus 1a, right? So these two decision will be added to our decision list here, then the m case will be completed. Okay. Okay. So r, so what we find for endpoint, rt is greater than or equal to m minus 2a, we decide. And if rt, we made a mistake, if rt, no, it's okay, it has to be otherwise. Okay, so this decision is completed. So this is the complete, this is actually for these are for in between points, this decision, what we can say, this in between points, inner points. Okay, so these are actually our inner points, these are actually our inner points, inner points, and this is for end point, end point. Okay. Okay, so all our inner points and end points can be actually summarized together. So these are end points, please write the inner points here, inner points. I'm not repeating here, so this will be the inner points decision rule, which will be the total decision rule, like all combination of m level. 2 is here, m minus 2 level will be this part, like this part. So we have the decision rule now. So this is our standard procedure. We finish the transmission, we complete the reception, we decide that. Now it's time to find the probability of error. So probability of error for our this m array system, m array PAM system. Okay. Now, say how to, when the probability of, or when the error happens. Let's see when the error happens. Okay. For example, this is minus a. This was a. This was 3a. Okay. So in between boundary, this is twice a. This is 0. Okay. So now we will have an example. Example that, okay, we are transmitting a0 equal to a. Okay. So consider a transmission a0 equal to a. This is we transmitted. Okay. So now decide how the A will be decided. A0 equal to A. Anything in between, is received, we decide as A. So the story is, we transmitted this constellation. In the reception, we receive any value in between this region from 0 to twice A. If anything is received between 0 to twice A, it will be received as A, right? So decide A0 equal to A when, if that is our condition previously. For example, the first condition, probably A0 equal to A. So this is the condition, 0 to twice A. So RT is greater than 0 between twice A. If this is the condition, then it will be received correctly. Here it will be received correctly. But if not, what happens? Or when the error occurs. So if error occurs, error occurs uh, error occurs if either two ways error occurs. Either RT is greater than twice A, or RT is less than 0, isn't it? Then this constellation will be received wrongly. It's supposed to be in this region, right? Then it will be received correctly. So two condition, error occur if RT is received as twice A, because our transmission was A. So if received, RT will be received wrongly if it's received RT is more than twice A, or RT is less than 0. Either this region it will be received as error, if in this region it will receive as error. That's I'm trying to say. Okay. Okay. So we will try to write it that, okay, probability of error. So probability of error P probability of error happens when the probability that RT uh, is less than 0 with union that RT is greater than twice A. This is the summary of our previous statement. This is the summary. RT is twice A or RT is less than A. If this condition happens, then the error occurs, which actually we express by this. Okay. So here we can say, for example, this is a one function, this is another function. Let's give it a name, phi 1. Say phi 1. Say phi 2. So probability, our RSP, from RSP formula, probability of phi 1 union phi 2 is nothing but probability of phi 1 plus probability of phi 2. Here the phi 1 and phi 2, there are two characteristics. The probability of RT is less than 0, or probability of RT greater than twice A, they are actually disjoint event. They are actually mutually exclusive. If this happens, that do not happens. If that happens, this do not happens. It happens either way. Like when we transmit a signal, for example, we transmitted a signal A, either I receive the signal here, or I receive signal here. We do not receive signal in two places, right? Either we receive signal in this region, either way signal is in this region, means they are actually, this condition is a exclusive, mutually exclusive. Yes, I'm trying to say. So uh, so these two, they are two event phi 1 and phi 2 are mutually exclusive. There is actually disjoint event. They are actually disjoint event. Disjoint event. Okay. So we can write or rewrite it, probability of error. Okay, do not have to write this way. We can just write directly, probability of error is nothing but the probability that rt is less than 0. This formula, I'm implementing this formula here, and probability that rt is greater than twice a. Okay. Okay, so now I will write it two other ways. So rt, we know rt equal to a0 plus n tilde. A0 is a. ep was there, ep was like, ep was there, ep is unity, so I'm not writing it, plus n tilde. So if this happens, that rt is less than 0, rt is less than 0, then we can write rt is nothing but a plus n tilde is less than 0. We find n tilde is less than minus a. Okay. Or so two condition error happens. If this is the condition error happens, this is the condition also error happens. So for this one, again rt equal to a0 plus n tilde, and rt is greater than twice a, right? So we know that rt is greater than twice a. Rt is a0 plus n tilde is greater than twice a, means n tilde is greater than a. So we find two condition. This is a condition. This is a, so n tilde is less than minus a, and n tilde is greater than a. So if this is the, if this condition, the error will happen. If this is the condition, error will happen. Okay. Now we will see it in a so both are error happens. This is error condition. Error happens for both condition, this one and this one. Now we will okay, I like to rewrite it. So pe is error when n tilde is greater than a, plus probability that n tilde is less than minus a. Let's draw the probability density function for this condition. Let's see this guy in PDF. So this is a Gaussian distribution with mean 0. Here mean equal to 0. This is the probability density function. This is a symmetric. this probability density function is symmetry. Okay, see, probability happens is n tilde is greater than a. So if this is a a, then probability happens if if uh, n tilde is greater than a. It also happens if is less than this region. Okay, this condition. This is this condition. This is this condition. So we can say this probability density function is a symmetry uh, in symmetry with reference to zero to mean with reference to mean value. This is a symmetrical value. So what it will help us, we'll actually find only one of the side, we can have the other one. So n tilde is a Gaussian with zero mean, right? And which is a symmetry around zero, means this will give us that two probabilities are the equal. So what will it gives us that probability of n tilde greater than a is actually equal to probability of n tilde less than minus. They're equal. They're equal probable. Right? So by symmetry, the left and the right trail probabilities are equal. So we can say here the by symmetry left and right tail probability is equal. That's how we write it. They are symmetry. Okay, if they are the symmetries, what will be the probability of error? Is nothing but twice of the any of the we can write any of the probabilities. So n tilde is greater than a because they are equal. Okay, so n tilde, we know what is n tilde, is a Gaussian mean with mean 0 with variance n 0/2. So n tilde is nothing but mean Gaussian. I have written it many times. Mean 0 and variance is n 0/2. Okay, so we can write this probability again. So if this is the case, so twice probability n tilde divided by sigma is greater than a divided by sigma. Just rewriting it. You see here, we can see that this is a standard Gaussian. This is a standard Gaussian. Remember standard Gaussian? I have discussed standard Gaussian in the very beginning when we discussed about AWGN, additive white Gaussian noise characteristics. Then there I have discussed this standard Gaussian. So in standard Gaussian, the mean is 0 and variance is 1. That is actually that how it makes it standard Gaussian. Okay, so in standard Gaussian, if this is the case, then there I write a formula. Probably you can recheck in our AWGN lecture. So the Q function x will be the probability of standard Gaussian then x. This is the solution for a standard Gaussian, right? So we will actually implement the same here. So we can rewrite twice q a by sigma standard Gaussian. So okay, I can rewrite it twice of q. Okay, not rewriting it here. I will write it here. Twice q a by sigma. That's for standard Gaussian, but I like to write the solution here. And 0 by 2. So this is the probability of error for the internal points, right? For inner points or internal points. This is the probability for inner points. So we yet to find the solution for the endpoints, right? So we only find the probability for internal points. Okay, so let's find the probability for the endpoints. Let us redraw the endpoints stuff. Let's see how it look like. So this is probability of error for, let's say, internal. This is for internal points. Okay. For endpoint, remember how we find an endpoint? Our endpoint was, remember what was our endpoint? Our endpoint was m minus 1a. Of course, the previous point would be m minus 3a. The boundary, okay, the endpoints will also be the this one, minus m minus 1a. I'm not writing it here. We'll do only one. So the midpoint is m minus twice a. So we will have a right decision if rt is this way. We will have a wrong decision if rt is this direction. Like for example, rt is less than m minus 2a, then the error happens, right? Error for this point, for this constellation, right? Okay, so how to find the endpoint? So consider m minus 1 a was transmitted. If this was, then a0 equal to m minus a. This was the right detection, right? If this is the right detection, then rt, the received signal, will be nothing but the received constellation plus the noise. Okay, so error happens if, so error, what is when the error condition? Error if m minus 1 a plus noise is less than the m plus m minus 2, m minus 2 a. See here, this condition. So error happens if m1 plus a, this constellation which was transmitted, that's why in the receiver side noise is added, is less than this boundary m minus 2a, then this side it goes to this side and the error happens. Okay, so n tilde is directly just solve it. A, so what is the probability of error? So probability of error is probability that n tilde is less than minus a. Of course, this is for this point, huh? For this point, endpoint. There are two endpoints. This is also an endpoint. For this point, this will be the symmetry. Same thing like previous, because of the mm, because of the because of symmetry. What will happen? Probability of error will also be same as probability that n tilde is greater than a. Because of symmetry, I'm not writing it. We also see the symmetry condition for our inner point. Okay. Okay, so probability of error is the probability that n tilde is less than a or greater than a, both. Okay, n tilde is greater than a. Okay, this is also a condition, so I will do the same thing as we did previously. So probability that n tilde divided by the sigma is greater than a divided by the sigma. Here again, this is a standard Gaussian. Gaussian. So apply the same rule. So for the n point, the probability of error is nothing but the q function a by sigma. So this is actually our another solution for n point. N point or yeah, n point. Those are the solution for in between points. Inner, this is end point. So this is PE end. Okay, like end. PE end point. Now here we will find their probability together. For that we will assume that all the points are, so we are assuming that points are equiprobable. All the points, whether it's end point, whether it's inner or in between points, they are equiprobable. Okay. Okay, what is the probability? What is the probability? What is the probability of a0? A0 is everywhere. So a0 is nothing but, we know, plus minus twice I plus 1 a. What is the probability of a0? A0 have how many level? M level. So what is the probability of a0 is 1 by m. What is the probability of n point? N point, we know only 2 n point. What is the probability of m point? Is 2 by m, isn't it? So what is the probability of inner point? Inner point. So 2 left, right? If there are total m, but 2 is the end point, so in between points are the inner points. So this by m. This is the probability, right? So what is the average probability then? So you see the endpoint probability and inner point probability, they're different. So we have to find the average probability. So average, for example, average probability of error is nothing but the probability of E error of endpoint to probability of end plus probability of error of the inner point, like inner or intermediate. What do we say? Inner. Okay, inner. The probability of inner. Inner, or how do we write previously? Oh, it's inner. So inner. Inner. Here you see the endpoint, probability of endpoint and probability of the inner points, they are what? Mutually exclusive. Exclusive. As we discussed earlier, same thing. So we can write it probability of n. So thus substituting the previous solution. Just solve the equation. We will end up solving the equation. We will end up this. So here our probability, average probability is twice 1 minus 1 by you remember what is A? A was 3 ES symbol energy, symbol energy m square minus 1. So we find the average probability of. Now we will replace this A value here. Okay, so we will replace this A value. Sigma is in 0 by 2. Sigma square is actually in 0 by 2. That's we replaced it here. So okay, can we further solve it now? This is actually our final probability of. Interestingly, this is for M level. This is for what? Probability for error, average probability of error for M PAM, pulse amplitude modulation. Okay, now let's say M equal to 2. What will happen this probability of error? You see M equal to 2, M equal to 2, 1 by half, 1 minus half, 2 to cross Q. So we can find it will be nothing but Q twice E S by N0, right? So ES 6 N0 M equal to 2, 4, 4 minus 1, 3, 3 into 6, so 2. So this 2. So do you remember what is the probability of error for which one? BPSK. So if M equal to 2, then this same formula goes to our very basic BPSK modulation. So this is the generalized M array. So if M equal to 2, then our solution checks out. Remember? So what is the point? In BPSK, we can use only 2 levels. In M PAM, we can use multiple levels. So what is happening here is one symbol, a symbol can carry multiple of bits. If it's M equal to 8, it carries 3 bit. If M equal to 4, right? So you see, you can increase. It can be like 4 PAM, it can be 8 PAM, it can be 16 PAM. So by increasing the symbol size, we can actually increase the data rate, which is actually the application for PAM in high speed communication, for example in 4G or other high speed wireless communication. So this is a very practical use for high speed data rate. Okay, so we can use multiple bits in a single symbol so that higher data rate can be achieved. Okay, that's all for this. Thank you.